be in for prayer.
Okay.
Dear Lord, thank you for this day, and please help the caffeine in my bloodstream to make it my brain so I can speak words today. Amen.
Amen. I hear that. Oh no.
So,
oh no.
picking up from where we were last time we did theorem 5.12, so now we're on 5.13. So if this is the family of path components of the space X, then for each n greater than or equal to 0, the relative homology group with respect to the subspace A of X is isomorphic to the direct sum of the nth homology groups of its path components with respect to the subspace A intersect each of the path components.
So cool.
So they just say proof use exercise 5.12 and theorem 4.13. It actually takes a bit more than that, but Rotman likes to delegate out his proofs to us, so see how far we can make it here. If I've done this proof correctly, I think you also need the second isomorphism theorem, so we call, if you have B and C are subgroups of A.
Well, that'd be understandable if he didn't cite that. That's just kind of like,
Right. But then you also need to use this from Mark here, which is from the beginning of page 91. If you have the singular complex of space, I guess that'd have to be isomorphic, maybe. But anyway, it's isomorphic to the direct sum over the singular complex of its path components. So together with that, exercise 5.12, which says essentially
where's that stupid thing?
The homology group of the direct sum is equal to the direct sum of homology groups.
Okay.
And theorem 4.13, which says that the nth homology groups of space is isomorphic to the direct sum of the nth homology groups of its path components. We'll start from the left side, work to the right. So, sum over lambda, hn of x sub lambda, comma A intersect x sub lambda. Remember, that was defined sum over lambda, let's see, it was the nth homology group of S star x sub lambda quotient S A intersect x sub lambda. So actually I think they proved the second isomorphism theorem in one of the exercises for complexes.
So where is that coming from? I'm sorry, Nathan. I'm just trying to follow along. What you just wrote in purple.
I believe is the definition of
definition of
the
relative homology
group.
Okay.
Right. I think that's on page 96. Yeah. Hn of x comma A is Hn of S of x mod S of A.
Right.
So, yeah. Using the second isomorphism theorem for chain complexes, term-wise here, this is isomorphic to the sum over lambda of Hn of, I guess, x sub lambda direct sum A mod x sub lambda, right? Let's see here. And I guess you could argue that that's isomorphic to just, might be missing something here. I think you could argue that's just isomorphic to path components, right? Because, no wait, that's not right.
I'm not sure yet.
That wouldn't make sense.
So the A quote unquote is the S star X sub lambda. But it's not, it's S star of the intersection of A and, I mean, I guess my trouble is you've got B intersects C.
Oh, right, yeah.
Whereas here you've got S star of A intersect lambda.
Yeah, that should be...
Is there a reason that S star of A intersect X lambda would be like S star of A intersect S star of X lambda? Would that even make sense? I don't know.
Well, I think what we have to do is this. Does that make more sense? Let me go back to where they have the second isomorphism theorem.
Yeah, should probably look at that. Just trying to understand the pattern here.
So they say if S prime and S prime prime are subcomplexes of S, then S prime mod S prime intersect S prime prime is isomorphic to S prime direct sum S prime prime mod S prime prime. So here we've got this. I guess you also need that this is isomorphic to S star A intersect
Yeah, that's what I was
S star X sub lambda.
wondering.
I think that's actually definition, because remember we do intersection is termwise.
Huh.
But so if you have that, then the second isomorphism theorem for chain complexes says that this is isomorphic to...
Huh. So how do you decide? It's weird. So like when you look at this, maybe I'm just not well versed in the second isomorphism theorem. I mean that's true. How do you decide which one's B and which one's C in that? Like B intersect C versus C intersect B. Is it also true that it's isomorphic to A plus C mod B? Just dumb question.
What was that?
I think so.
Well, if you look at the theorem, you know, A mod B intersect C, I could just as well say A mod C intersect B. So that would also be isomorphic to A plus C mod B. Just
Actually, that might not be correct. I guess it's only between two groups. Right? Two groups that are the subgroup of the same group. So that should
I think
be...
that's true. Yeah.
Yeah, so I wrote this incorrectly. This should be A intersect B. A plus B mod B, I think.
Yeah, I think that's right.
Yeah. So I think that does give us this though, right?
yes.
Yeah.
Yeah, I signed that the abstract the other day. I have to do that Friday.
So
Huh.
and I guess that's just isomorphic to this.
Sorry.
Yeah, that's right.
Okay, now the pattern gels for me. Yeah. Okay.
Yeah. So then, by exercise 5.12, this is isomorphic to Hn with sum over the path components.
How do you get from the last purple statement to that one? I'm sorry, Nathan.
This to this.
No, before that, like the complicated thing up there to the next line. Or you don't. I don't know. Like if
I mean,
so what is that?
it's like the direct product when you're modding out one of the terms, right?
Right.
It's like I can't
Oh, you're just using you're using just basic isomorphism.
Right.
Oh, I'm sorry. I see it now. Never mind. I'm asking you why did you cancel 1 with 1
Yeah. So here,
or 0 with 0? I guess. Mm-hmm. No.
we pull out the Hn.
Let's do that. Except
So
in
we
the
just
extended
get
complex.
sum over the
Even that, be careful.
singular complex over path components. And so by what was it? Oh, I guess just by the remarks on page 91, this is isomorphic to Hn of wait. What are we doing here? No, okay. I think I'm confused. This is the internal direct sum in the theorem, right?
Uh-huh.
This is going to be a subcomplex of this because this is a subspace, right? So this whole thing is just going to be isomorphic to S of x sub lambda mod S of A.
Yeah.
Yeah. That's what we need to do.
Right. Yeah, I'm sorry. I mean, what I should say is right. Yep.
And then this now,
Oh, goodness gracious.
pulling the Hn out. This then, let's see, what are we trying to get to? We're trying to get to H sub n of x comma a. So H sub n of xa is defined to be H sub n of S of x mod S
Don't you just want to leave the sum outside?
A.
Yeah.
Nathan, you just want to leave that sum outside because then, by your definition, Hn of the quotient of S star x lambda by S star of A, that is the relative homology that you're trying to get to. Like, just don't bring the sum inside. In fact, I think you can conclude from your last statement, actually.
Well, we need
Well, he's trying to
to
get to Hn of xa.
get to
H-
x. Right now we have the x sub lambda, so we need to bring those together somehow. Right?
It's going from the right to the left.
Oh, I'm sorry, Nathan. I was thinking you were going from left to right.
Okay, yeah.
that would explain why I was having an easier time of it.
So, now that we have this,
Sorry. Oh, okay.
I think we can argue that this is,
So it's like S star of the sum.
well, this here, right?
Right.
This is just, you're right,
S star of x.
S star of the sum,
Yeah.
which is x.
Right.
and then
And that's what we want.
that's equal to
Oh, very good.
hn of x.
Okay.
Alright. So it took a while, but we got it. We got it moving.
Take your time.
Alright. So
Ow.
next we have this corollary here, and this is essentially the useful part of this theorem.
Oh.
Essentially we're showing what we showed with regular homology groups. So this is corollary 5.14. So corollary h naught x comma a is free abelian, and the rank of that group is going to be, I'm not going to say card because it's kind of weird notation. I've never seen it anywhere else before. But yeah, the cardinality of this set. So essentially this is the number of path components that are disjoint from A. So proof. So that's kind of intuitive since in the usual case it's just straight up number of path components. So proof here, by the theorem we just proved, h naught of x comma a isomorphic to the sum over h naught x sub lambda a intersect x sub lambda. So we have the intersection between the two is empty, then we know h naught of x sub lambda a intersect x sub lambda. This is just going to be empty set. So by those remarks we made last time, this is isomorphic just to h naught of x, which is, they put equal, but I think it's actually isomorphic to z by theorem 4.14. So then, if on the other hand, the intersection does not equal 0, or the empty set I should say, then we have h naught of x sub lambda comma a intersect x sub lambda is equal to 0 from theorem 5.12 if x is path connected and A is a non-empty subspace, which is what we have here, then h0 of x comma A is 0. So there you go. Because we've shown that this sum here contributes a factor of z for every subspace that does not intersect with A, and gives you a factor of 0 for every subspace that does intersect with A. So our rank is the cardinality of this set. Alright, so our next corollary here is really simple.
So it's saying that if the, let's see, put that in the words, the number of path components is...
Number of path components, well, number of path components that are disjoint from the subspace A is the rank of this group. Does that make sense?
So A doesn't, so like if A is in a particular path component, then that one gets, that one's lost?
Yeah. So for example, if you had something like this,
So if A is in that
And-
cheese puff. Oh, A's and 2 cheese puffs.
This is A.
Uh-huh.
Then the rank of so if this whole space is H, then
And the rank's gonna be 1.
right, exactly, rank of H naught XA is 1. Because
A gets path connected to everything else there, and so it's
right.
it.
It doesn't have these two path components,
I mean, A is
X1, X2, X3, do not have an empty intersection with A.
I'm just trying to intuitively get some
Yeah, I
feeling
guess.
for what is HNX comma A anyway. I mean, this is the relative homology group. I mean, what is that? It's
We'll actually get to that question in a second here.
Well, I will shut up.
So, but that is a good question. So this next corollary here, 5.15, we're essentially applying it to the zeroth relative homology group with respect to a point.
You mean 515? But yeah.
Isn't that what I said?
Oh, maybe you said it. Maybe it's just my brain.
I wrote down 5.
You wrote 515.
Sort of.
It's fine. It's fine. It's cool. I'll have to review the tape later. We'll find out who's right and who's wrong.
So if X is a space, base point X naught.
Hey, I edited something out the other day. Oh, by the way, there's a reason.
Was it
There's a reason, Nathan. We couldn't prove K divides N. It's not true.
Oh.
Oh.
I told Bill, and Bill's like, "Well, if you consider the homomorphism defined from Z4 to Z6 by phi of x equals to 2x, that is a homomorphism, and it's pretty clear 6 does not divide 4. So
Is it just that their GCD is not 0, not 1?
you have to if you do that, like now, Nathan, you're right. It has to if it's surjective. A surjective homomorphism from Zn to Zk has to have K dividing N for the argument we found. But we assumed that the image was K,
Right.
which I bought into. But then I tried to explain it to other people, not assuming surjectivity, and it all blew up in my face again. I lost last Thursday because of this. Anyway, sorry, I'll shut up.
All right.
Sorry.
Oh, you want me to take my time, so you have less time to talk today.
Would I do that?
All right. So
Would I do such a thing? No.
carrying on.
Surely not.
So H naught of X naught is free
See, you're closer to being a teacher than I realized.
Euclidean group of possibly infinite rank R. So with rank R, and we have, I guess, and X has exactly R plus 1 path components. So they have a proof here. I don't even really understand why they went through so much trouble.
Right.
Essentially, this is just counting.
Right, there's only one.
X naught can
component,
only
X
belong
naught can
in
be-
one component,
Yeah.
so you get rid of one of these, R plus 1.
Yeah.
There you go. So, that one's easy. Erase some stuff up here so I can move on.
Oh, yeah,
Oh, where's the...
yeah,
Yeah.
yeah.
Yeah, it's like he doesn't use 5.14 to prove 5.15.
Yeah.
Huh. Yeah. That's funny. You must be fond of this argument. Anyway.
I'll do it again.
Alright. Let's see what we're at next. Theorem 5.16. X be a space with base point x naught, then Hn of x naught is isomorphic to Hn of x for all n greater than or equal to 1.
Have you guys seen the new Legos? These new Star Wars Legos, they're amazing.
Different robot.
Alright. You want this to drag on, I want this to be over with.
It's too obvious.
Okay, so here we're actually using theorem 5.8. Remember, if we have a subspace, then we get an exact sequence for free, essentially. So we're just applying that theorem for the singleton x naught. So from that theorem, we obtain the exact sequence as follows. Hn x naught.
So is that the pointed homology? Like x comma x naught? I mean, what? Well, anyway, you said you were going to explain how to think about it in a second, so I'll let you.
Well, it's the.
It's a relative.
Well, I mean, it's isomorphic to.
Yeah.
Yeah. So I mean, there's no point really in making a distinction.
See what you did there.
Oh, I didn't even intend to do that.
Those are the best.
Actually gets
What can I tell you? I'm easily amused. So, an exact sequence, no less.
Right. It's exact. So, if n is greater than or equal to 2, then n minus 1 is greater than or equal to 1. So, by the convention axiom, so if n greater than or equal to 2, by dimension axiom,
Mm-hmm. Oh, cool.
we get, yeah, I thought this first part was a really neat argument. So we get 0, 0. Short exact sequence, right? Therefore,
Oh no, you put the
Oh.
left zero in the wrong place.
thanks. Yeah, I was confused with
Where's
that
the
makes
isomorphism?
that makes more sense.
Uh-huh.
So short exact sequence now.
No, it's an isomorphism.
Right, exactly. This is iso. So n greater than or equal to 2 is really simple. So if n is equal to 1,
Ooh, I need to make sure to define faithful action next lecture and connect it to God's faithfulness. I will get a better score on that. You know,
so here we're looking at the end of the sequence.
biblical worldview question. I will
Hn
we'll work it in.
x naught, Hn x. Oh, what am I doing? This should be H1. H1.
It's okay. Take your time.
H1. X naught. And then on to the H0. X naught. H0 x.
Ah.
H0 x naught 0. So here we're using one of the more technical exercises. I may or may not have gone over it. Exercise 5.2.
What is the first homology of a point, anyway?
First homology of point.
What is H1?
So if 0 is exact.
It's Z? That's wacky. So you're going from Z to H1x to H1x, x naught. back to. Oh, that's 0.
G, H,
Wait a minute. What's H not of a point?
F,
Yeah, it's not a point in Z.
Z again. Huh. Z's all around.
So, if this is exact, then F is surjective, and only F. H is injective, so we're going to use that here.
F is.
Since H1,
Now, you know
Like
this is.
that.
You know that this is exact by the that theorem I forgot the number of.
right, the exact
Yeah.
same theorem we used for this, theorem 5.8. We're
Right,
just looking at the
similar.
end of the sequence here. So, let's say we got H1 of x naught equals 0. Is anything else equal to 0? Let's see, I guess the labeling is important here. So this map is G,
I thought you said H1 of X naught was equal to Z.
H.
Sorry, H not of X naught is equal to Z.
Oh, H1 is 0.
Oh.
Okay.
Thank you. Wait,
No, sorry, it's
no,
not.
no, no, no. That's equal
H1
to
is
0.
0, yeah, that's true.
I mean,
H
Oh,
naught
there is no H naught of X naught. Oh, there is in the middle, right
Yeah,
there.
H naught of X naught is isomorphic to Z.
Z.
He talked about that later.
okay.
Oh, okay.
I don't
You
think
get-
there are any other zeros.
So here, applying this example, G is surjective if and only if H is injective. And so our end goal here is what? We want to show that these two groups are isomorphic. So our goal is to show K isomorphism, right? So,
Yeah, but
no, we're not doing that. We're
you want
doing,
N equals 1, right? You want
Yeah.
the G.
yes, we're looking for this.
And we already know that it's injective.
Right, because it's induced from the inclusion. So we want to prove that surjective. So to do that, we're going to show that H is injective. So this argument here is pretty interesting too. They say the map H has domain Z.
H naught of X naught.
Okay.
And target free abelian group H naught of X. So they say if H is non-trivial, then H must be injective. The reasoning they give for that is if the kernel of H were not equal to 0, then there would have to be a non-trivial subgroup of this free abelian group Z mod the kernel of H. But that would have to be a finite subgroup, which is impossible because this is a free abelian group, and therefore, if H is non-trivial, H must be injective. So that's the first part. The argument they give here is kind of backwards. So the next part is to actually show that H is non-trivial. So, actually the second part I don't really understand completely. They say if the image of H is equal to the kernel of K.
Well, that's true, because it's exact, right?
Oh, right. Yeah, I don't know why I put it there. So, see, kernel of K not equals 0 implies image of H not equal to 0. Okay, so we're deferring that to showing that the kernel of K is not equal to 0 by exactness. So then they say K being induced by inclusion is the map given by gamma plus b naught of x
See.
maps to b naught of x out gamma. And so, that part makes sense.
Mm-hmm.
But then they say, therefore the kernel of k must be equal to b naught of x, internal sum, s naught of x naught, mod b naught of x.
Mm-hmm.
And that I don't entirely understand.
Well, I mean, the coset. I think the coset's what, b naught x plus s s naught x naught. So if it's in there, that gets absorbed into that set. But mod, why mod bx?
Yeah, I don't even see how this is a subgroup of h naught of x.
I mean, s naught x naught is a set, right? Yeah, these are the zeroth chain complexes, right?
Right.
So, k is surjective, right?
Yeah, by exactness.
Right. So I think there might be like some isomorphism theorems that kind of go into that.
Hmm. Are you thinking using the second isomorphism theorem? Because that's kind of what I thought when I saw this.
I think so.
P naught of x. The domain here wait. Why did they say that? Oh. So they say the domain here is this.
Right.
Usually
S
that's
naught is z naught.
z naught, but
Yeah.
in this case, they're equal.
Mm-hmm.
So this is our domain.
Gamma's a cycle, right?
Right. Well, I think it's just a chain. Well, okay, yeah, it'd have to be a cycle. Yeah. Yeah, exactly.
So it's saying you can shift the cycle by, of course, a boundary, right? But also by something in S naught X naught, which I guess is a slightly surprising thing. Mod the boundary though. Eh. I guess that's just, I mean, that's mod the boundary, well, that's just what's in there anyway. I mean,
Hmm.
that's just saying.
Yeah, I don't know why they wrote it this way.
I mean, kernel.
I mean, isn't...
Yeah, I think that it can also be expressed as kernel K is equal to, say, alpha plus beta x naught, where alpha is taken from the boundaries plus S naught of x naught, right?
I mean, I think you could just write it as h naught of x. Because this is a subgroup of s naught of x.
I'm sorry, I should write that down.
So
It's hard to understand me
is
when I
just
say
going to
something
be
like
s
that.
naught of x.
What I'm saying is just that this set, I mean, maybe you already said this, Nathan, but I think you could say that this set is the same as, you know, alpha plus beta naught x, such that alpha is an element of beta naught x, b naught x, plus s naught x naught. That's just a notation for that particular set of cosets. You're looking at boundary cosets.
Right.
So really,
Wait, don't you mean Z naught?
well, the domain of K, right?
Like this S naught, this is in the range. Right?
It is.
Yeah. That's what it's mapping to.
Oh.
And we're looking at the kernel. I don't think that's right.
Well, how can that be?
Well, what I was saying was this is a subgroup of S naught of X naught. Oh, no, wait. X naught. So
I mean,
that's not true.
S naught mod B X naught. I mean, S naught is in the domain of K.
That's not of X.
Can you grab me my bag real quick? No, the grayish one. Shanku. I need technology.
Oh,
So
yeah,
this
S naught of
right here is the domain of K, right?
right.
So that's X naught. Oh. What?
Yeah. How's that?
What are they saying here? Huh. Where was I?
I mean, I think.
Hmm.
Yeah. See, I don't know what they're saying, but S naught of X naught is contained in S naught of X,
Oh.
which is
okay.
contained in B naught of X.
There we
Oh
go.
no, other way around. Oh no, okay. I don't think you can do what I was thinking because this is here, so you
But-
can't show that. So that doesn't work.
Hmm.
I was thinking this was just H naught of X, but I don't think it is. Well, anyway, they say that this is non-zero then, because B naught of X is described as the set of all chains with the sum over their coefficients equal to 0. And even that I don't understand what the reasoning is coming from, because I don't see how you can go from that not being 0 or this description of the coefficients to that not being 0, but make the argument, and that shows that G is an isomorphism.
Hmm. Yeah, it's definitely something I don't understand here. 'Cause I don't,
Yeah, neither do I.
I don't know why you'd. My understanding in the green may be wrong as well. I mean, I don't know why you'd write alpha in boundary plus S naught of X naught, because if you're working with a boundary coset, well then that automatically gets absorbed. Well, I guess that's just to say that's. Anyway, you can go on. It's fine.
So they do make the remark
You figure it
that
out.
because of this
No.
theorem, we can regard Hn as functor with domain the pointed topological spaces,
Mm-hmm.
because these are interchangeable.
I mean, you're awful close to having it. It's just this one last
Yeah.
thing. The argument about the
And actually in this next section here-
homomorphism from the integers into a free abelian group having to be non-trivial is interesting.
Yeah. In this section we're going to see how to avoid it.
Oh, okay. Well, then let's get on.
So, definition. If S star X, boundary is a singular complex of some space, we define S tilde negative 1 X to be infinite cyclic group with the generator, the symbol bracket, space, bracket. Which is kind of weird, but hey, let's roll with it. So then they define partial squiggle knot from S naught of X to S squiggle negative 1 of X, essentially by mapping n chains to just the sum over their coefficients times this weird bracket generator symbol.
Wow. I love he
So then
admits
they
that
define,
the algebra was fussy.
Yeah.
So we got
yeah.
stuck on the fuzzy algebra apparently.
It's not just that it's fussy, it's that he didn't explain
Yes.
what he did, which he does often, and it irritates me. I mean, I guess if I had more time, it would be a
Yes.
learning experience, but I don't have more time, so it's a
Yeah.
frustrating one.
Stupid liberal arts requirement keeping you from being broad in your knowledge.
So, let's see.
Where it matters.
Sorry.
I'm a specialist in
Where was I?
apologies. Let's see here. Where are we?
So the augmented singular complex is essentially the same as the usual singular complex of a space. So S2 of X, delta 2, S1 of X, delta 1, S0 of X, delta squiggle knot, 0. So they say it is a quick calculation that
Wait, delta squiggle
delta
knot.
squiggle knot delta 1 is equal to 0.
You forgot
And
to
it actually is a really quick calculation. I guess you probably already see it, right, Daniel?
put- I was saying you forgot to put the S squiggle -1 at, like before the
Oh.
0 in your exact sequence.
Before, you mean after? Yeah.
Yeah.
Thank you. Then you got 0. So this here, if you guys remember the definition here, right? Well, not of this, but of just the regular boundary map.
Yeah.
Sum over k equals 0 to n, which here is 1, right?
Uh-huh.
Negative 1 to the k. Ith face map
Yeah.
of sigma, right?
K-face.
Right. So, essentially here we get,
That's a K, but whatever.
oh, right. So we take this of this, whatever this is, this is a linear map. So this is going to map to this bracket thingy.
It's just
So
1
essentially you just get bracket minus bracket, 0. So this is in fact complex. They also say that S squiggle -1 of X. So, well, okay, yeah, that's from the definition. So let's see. So they also say they define the empty set to be the standard -1 simplex. It's interesting. So what else? I guess we have definition. So then they define reduced homology groups. Are going to be h and squiggle of x, which is just the nth homology group of the augmented singular complex. I guess they choose that. So now our theorem. So let me move over here. Nth reduced homology group of space is equal to the nth homology group of x comma x naught. So as a simple corollary to this is of course isomorphic just to the nth homology group of a space.
Well,
So that's nice.
oh, sorry.
That was what we just proved.
Yeah, well, we proved it for all n greater than or equal to 1.
Okay.
Where this says for all n greater than or equal to 0. So I think he uses that for the proof of this one. For n greater than or equal to 1.
Okay, so this is n greater than or equal to 0. So proof of this. What does he do here?
So he actually uses.
So most of his proof here is about n equals 0.
Yeah.
The part you put in parentheses is kind of like. That's what he uses.
Yeah, I guess that's what he uses for n greater than or equal to 1.
Since it's the same complex.
Yeah, that makes sense. So what does he do? If n is equal to 0, the end gives us a short exact sequence. And what does that give us? He says if alpha element S naught X satisfies partial knot school alpha equal to 1. And it's easy to see, footnote, that S naught X is equal to kernel of partial knot direct sum subgroup generated by A. And he says Y in the footnote there, which we probably shouldn't get into for time concerns. And because I would have to think about it to understand it again.
Yeah. I was wondering, when he says delta not squiggle of alpha is equal to 1, does that mean it's the bracket, like the generator?
Oh, good question. I guess it would have to be. Yeah.
Can I come in or not?
Or in the middle of something.
Okay.
Yeah. All right.
Yeah.
So from that he has h naught of x. By definition is s naught mod, while using the fact that this is equal to z naught of x. So then you get this clear fact. Alpha mod v naught of x is isomorphic to the kernel mod v naught of x direct sum z, which is equal to h naught of x direct sum z. So since h naught of x is free abelian, the result follows from corollary 5.15. This should be squiggle. Wait, how does that help us? 5.15.
That's the rank corollary.
Isn't that the one we understood?
Yeah. So it says that the rank of h naught of x is going to be the number of path components minus 1. Okay, so plus 1. Oh, okay, sorry. So we're trying to show.
We're trying to show that
of
it's
x.
isomorphic to h naught of x comma x naught.
And we know that the rank of h naught of x comma x naught is going to be the rank of h naught of x minus 1.
Mm-hmm.
So the rank of h naught of x is going to be the rank of h naught of x comma x naught plus 1. So that's why there's there's an extra z.
And then it's free
So,
abelian.
right.
Okay. So that's why I was forgetting the fact that it's free abelian. That makes sense. Alright, so this next corollary here is kind of technical, so I won't get into the proof of it. Essentially, it gives us a basis for the reduced homology group. So corollary 5.18. Lambda, x sub lambda is the family of path components of x as before. So if we have a choice of points x sub lambda in each of the path components, then the class of x sub lambda minus x naught, where x naught's base point, with lambda not equal to lambda naught, which is the path component of x naught, is basis for h naught squiggle of x. Alright, so now finally we get to the point I was talking about.
Interpretation.
Which actually, I don't think they prove here. But they say here, this first paragraph on page 104 after the exercises, that for nice subsets of a polyhedron,
Mm-hmm.
you have the relative homology group with respect to a subspace is isomorphic to the augmented homology group of x mod A. So this kind of makes the